All right, welcome back to the dedicated section of students who are willing to make it to lecture on Friday at 9 a.m. So we talked a lot about non-invertible symmetry in 2D, and there is actually a lot more we could do there. I just told you about the ground states. I could have told you about some representations, about scattering. There's a whole continued subject there. But I thought that just to give you a taste of the landscape of this field, for the last two lectures today, we will jump from 2D to 4D. And part of the reason for that is that many of you might think that 2 dimensions is very special. There's Virasoro, maybe the models are solvable. If the only examples of non-invertible symmetry that we had were in 2D, I think the subject would indeed be rather limited. So instead, I'm going to show you some non-invertible symmetry in real 4D gauge theories. I'll give you the simplest examples. The first example will be exactly solvable, but the next not. And so that will be kind of proof of principle that this concept is useful even above 2 dimensions. Okay, so today's first lecture, remember you got me twice today, so buckle up, is free Maxwell theory in 4 dimensions. 4 space-time dimensions. So S is 1 over 2 e squared integral f wedge star f. And apologies to Nathaniel, but I will never be able to get the indices straight if I put it. So star f mu nu is up to some 2's that are pesky. Okay, so that's our action for the first lecture. I have not canonically normalized my gauge field. I've put the coupling out front. And what we're going to show is that this has non-invertible symmetry if e squared over 2 pi is any rational number. So that should be a pretty weird statement, right? First of all, I'm telling you that a theory that is 100 years old and maybe has some new symmetry that we didn't really know about until a few years ago. And second of all, it depends on this very strange condition on the coupling. Okay? So it's rational. E squared over, e squared over 4 pi. So I just an additional 2 there. Yeah, so that would count. If it was literally 1 of 137, there would be something special to say. Okay, so 2 comments. We'll have lots of comments, obviously, and we're going to kind of derive this as we go along today. But first comment is this is some codimension 1 topological operator D. So it's something that could be put on a 3 manifold. For instance, that 3 manifold could be all of space. And the second thing is just coming back to belaboring this point. This is fixing the coupling. In other words, f wedge star f is charged under D. Right, so usually you think there's no ordinary symmetry under which the Lagrangian density is charged in Maxwell theory, but we're going to find some symmetry today. Yes? How should you think about whether you can determine e squared over 2 pi is rational? Well, the conservation of this operator predicts very special degeneracies of the theory. Okay, not in flat space we know the spectrum exactly, but suppose you put it in some cavity with some boundary conditions. Okay, then you can study the spectrum, and the spectrum will have some degeneracies predicted by this operator, and you could try to verify them, and they would change depending on what the rational number is. So one of the things that is not obvious from what I said is what's the relationship between nearby rational numbers? Actually, the symmetry is totally different, so the predicted degeneracies would be quite different. So there's not really any smoothness there. Okay, so this is what we're gunning for, and the key tool that I'll first teach you about. We're going to need to build up a lot of structure here. Yes?
As the coupling gets renormalized, do we expect it to change?
There is no renormalization because this is a free theory.
Oh, I see.
And so E is a very meaningful concept here. Okay, good. More questions before I dive in? Yeah?
If E was like the VEV of a scalar field, like if there was some kind of dynamics happening, would like the non-invertible symmetry have any effect, like causing the coupling to get locked onto a rational value that like hit it as it rolled?
If your ultraviolet model preserved the non-invertible symmetry, for sure. That's one of the reasons why I emphasized this point. Okay. All right, so we're going to need to build up some structure to derive this result. And so our first key tool will be electric magnetic duality. Okay. So classically, this is just the transformation that E goes to B using non-relativistic notation, and B goes to minus E. And classically, it is independent of the coupling. When you talk about classical physics, all you're using is the equations of motion. E is an overall prefactor and drops out. So this doesn't know anything about E. I'd like to spend a few minutes deriving the quantum analog of this statement for you, because we're going to use the details. So we're going to derive the quantum analog by changing variables in the path integral. So the first thing is, in the functional integral, we usually think that we're integrating with respect to the gauge field capital A. This will be my notation for what we're integrating with respect to. And we're going to change to instead integrate with respect to the field strength. So that's our first trick. Now, if you treat the field strength as an independent variable, you need to make some modifications, because the field strength obeys some identities when it's viewed as d of A. Okay, so F is the independent variable. And we know that dF is 0. So F is not arbitrary. So we're going to enforce that with a Lagrange multiplier. Okay. So our action, so the Lagrange multiplier will be called A tilde, and the action now must be 1 over 2 E squared integral F wedge star F. Now we forget the fact that F is dA. And now I add to the action this coupling. Okay, and we're going to integrate dA tilde and df. Here also I should say I integrated this term by parts. The Lagrange multiplier A tilde is supposed to enforce the equation of motion that df is 0. So I moved the d onto A tilde. Yes?
Are there any subtleties in the path integral having to do with like Jacobians or so in the measure?
There are tricky things like Jacobians you need to keep track of. I will mostly ignore them right now. They're not going to be needed, but they are important for some purposes. Yeah. Okay. So so this derivative coupling. Let's inspect this some more. This derivative coupling of A tilde, the fact that the action depends only on dA tilde, not A tilde, this tells us that A tilde is a new gauge field. And I will enforce that its fluxes are quantized. Let's call this n in the integers. Any n is allowed. This also explains how I got that very particular coefficient between A tilde and f. Right? I put a very specific number there. Where did it come from? So let's check the coupling. So in particular, when we do the path integral over A tilde, we're going to sum over fluxes of A tilde. So schematically, what will that introduce? There will be a sum over n. N is this same integer n that I introduced here. And that term dA tilde wedge f now becomes this term. Right? Two of the dimensions got sucked up by having the integral of A tilde be n, and the other two are integrating f. Okay? Now we have a sum over n here, and this is going to give us a Dirac comb, a periodic delta function. So it's a sum over integers m of this delta function. So what that coupling is doing is enforcing properly that f is quantized. The fluxes of f are quantized. Okay, so that you can see now that I've introduced my Lagrange multiplier properly. The integral over A tilde really does enforce all the identities that we wanted on f, namely that it is closed and it has quantized periods. Yes? For instance, you could imagine on S2 times cross. The question was, am I doing the path integral on S2 cross S2? You could imagine that if you want to see this quantization condition most strikingly. Yes. More questions? Yes? I'm enforcing that separately so that the path integral doesn't just give infinity automatically, right? If I shift the action of if I shift A tilde by a gauge transformation, then the action is invariant. So if I don't treat A tilde as a gauge field, I just have a big infinity. So I'm trying to cook up A tilde and its couplings such that the integral over A tilde and f is equivalent to the original integral just over A. Yes? Yes, it still works. There's more questions about this. Let's follow up on that detail afterwards. Okay. Okay. Let's keep going. Let's try to investigate why is this related to duality. So A, we know, couples to electric charge. But as I will now show you, A tilde couples to magnetic charge.
Sorry to go back. One quick question. You're integrating a total derivative of A tilde here, and upstairs you dropped the total derivative and integrating by parts.
Yes, right now the question is about what about the total derivative. I'm imagining that my space-time is either compact, like a big 4 sphere, or S2 times S2, or whatever you have, or I've put some boundary conditions at infinity. Okay, so let's try to see this. So let's have a magnetic monopole of charge M. I'll try to stick to my M's and N's consistently. So that means that the integral of F is 2 pi M. So what's the picture? Here's the monopole in space. Here's some 2 spheres surrounding it. And that's that 2 sphere there. So this is a 't Hooft line or a magnetic monopole, whichever language you prefer. And let's try to pin down, let's be a little bit more specific about where it is in space and time. We could do this for any line, any world line of the monopole, but let's just choose our coordinates nicely. Let's say the world line is gamma, which I'll just take to be t, and then the origin in time times space. Okay, so imagine we have such a configuration. Let's see what this cross coupling there becomes. Okay. So we have I over 2 pi integral dA tilde wedge F. This is I over 2 pi. I'll separate the variables. We have an integral over T and R of dA tilde. And then we multiply it by the integral over the angular 2 sphere of F. Okay. And now we just plug in what we know. And this is I m integral over T and R of dA tilde, or integrating the R direction by parts, I m integral just over the world line gamma, which is the T line at the origin of A tilde. So this looks like a Wilson line. But for magnetic charge. So that was the thing I wanted to show you. Okay, we're almost done with the electric magnetic duality. But what we need to do now is integrate out F. So now our next step is to integrate out F. And we get to do that using the equation of motion and substituting back in. Everything is quadratic. Right? So what is the equation of motion? The equation of motion says that F is equal to E squared over 2 pi I star dA tilde. And this dA tilde we could call F tilde. So we take this equation of motion, we substitute back in. What do we find? There's a limited amount of algebra that I can still do, but this amount of algebra I can. So we have 1 over 2 e squared integral f wedge star f. Here is f. We're just going to rewrite f in terms of f tilde. E squared on 2 pi I star f tilde. E squared on 2 pi I f tilde. Remember, star squared is 1. That's the double contraction with epsilon. Then we have our cross term, I over 2 pi. We had dA tilde directly, so that's just f tilde. And then we have f, and f is that. Okay. And these terms are the same. You have f tilde and star f tilde in both of them. You just need to collect the coefficient. We will decide to write it as 1 over 2 e tilde squared integral of f tilde wedge star f tilde, where there's a new coupling e tilde squared over 2 pi is equal to 2 pi over e squared. That's the nice formula that you get. Okay, so the action takes the same form, but the coupling has changed. Any questions about that derivation before I make some comments? Okay, so some comments. First, this is an example of a strong weak duality. What I mean, of course, is that if E is very small, then E is large. Duality is generally not a symmetry. It's just a distinct of our same fixed theory. And we'll try to understand what's in this weasel word generally soon. There is an action on the one-form symmetry of the theory. So the one-form symmetry, QE, I won't put the coefficients, was like the integral of star f, and QM was like the integral of f. Hotat gave you many beautiful lectures about that. And duality on the pair QE, QM equals QM minus QE. Right, that's the E to B switch. But we can say that it's an action on the symmetries, the currents of the model. And finally,
For this to be an explicit duality, should we not get a term which would be the analog of the Lagrange multiplier in the final action?
no. So the question was, why didn't I get the Lagrange multiplier in the final action? View this as some kind of intermediate step. Okay? So what I'm trying to relate is the initial action with A alone to a new action of the same form with A tilde alone. The Lagrange multiplier is the cute intermediate step. It's like field theory version of Fourier transforms. There is an interesting special point. This is my last comment. E squared over 2 pi equals 1, which is self-dual. And this will be a clue towards the general structure that we are going to uncover. So keep that in mind. Okay, so we finished our lesson on electric magnetic duality. That is our first tool. Any questions about it? Yeah. Yeah, good. So, I mean, this is a free theory, so it can be exactly solved. But I meant in a more in an interacting example, it would be like a strong weak duality. Yeah. Same question. Okay. All right. Great. Okay, so that's tool 1. Next tool is about gauging one-form symmetry. You heard some lectures about this from Hotat, so I can be somewhat brief. Okay. So let's go back to the free Maxwell theory, and let's couple it to background fields. So this is the action coupled to background field. So BE and BM are two-form backgrounds for what? The electric one-form symmetry and the magnetic one-form symmetry. I don't know if Hotat used that notation, but it's pretty self-explanatory. Just U1 times U1 for electric and magnetic, and the 1 reminds us that it's a one-form symmetry. Oh, there's a secret SPT there. I'm not gauging anything. So far, I've just introduced sources, right? So the question was am I gauging something? That's what we're going to talk about in a minute. But for right now, they're just background fields. So they're just widgets that you can vary with respect to derive correlation functions. Okay? Now, coming more directly to that question, there is an anomaly of this one-form symmetry that you heard about. And that implies that you cannot simultaneously gauge BE and BM, or at least all of them. But it's a mixed anomaly. So let's consider gauging a discrete subgroup, Zn, that lives just inside the electric part. Because the anomaly is mixed, this is allowed. Okay, so I'm going to take this action. I'm going to set Bm to 0. I'm going to let Be be dynamical, but with very restricted holonomies. Right, it's going to be flat, and it's only allowed to have Zn holonomy on surfaces. Okay? That's what it means to make that dynamical. So I claim, this is our next sort of lemma that we need, is that the resulting theory, after doing that, is again Maxwell. With the substitution A, the dynamical gauge field, replaced everywhere by A over N. Or N is this N. Let's leave this here. So there are various ways to skin this cat. I will do the least formal. I'm going to derive this by examining line operators. So let's consider the Wilson line, WQ. Q is integer. So this Wilson line has charge Q and Z under this U1 electric one-form symmetry. Okay. Now, what happens to this Wilson line when I gauge the Zn subgroup here? Well, then this Wilson line is charged in general, and so is in general not gauge invariant. So WQ is not gauge invariant. Unless Q is 0 mod n. So in my new theory, I throw away some of the Wilson lines. Now, Dirac quantization what does it tell us? It tells us that the minimum Q electric times the minimum Q magnetic is 1. So when Q electric is 0 mod n, this allows new magnetic fluxes Qm, which are fractions with denominator n. Okay. So that is exactly the same as the lines that you would get if you naively just rescaled the connection by a factor of n, right? The fluxes would go down by a factor of n, and the allowed integer charges would have to be multiples of n. So that is what I wanted to show you. This derives this fact. Yes?
Why the squiggle?
Oh, I just meant that I don't want to write that they're the whole technically precise thing, that they're fractions with denominator 1 over n. This is the minimum one, you should say, or q min is 1 over n. Yes, Sanjay?
Is there a way to see the existence of these new magnetic states in terms of the original field variable?
Yes, that is a good question. So the question was, how do you actually technically construct the new magnetic states? And that is where I'm sort of doing the least formal, we're biting the bullet by doing the least formal thing. It's not going to get us there. If we really wanted to do that, we'll have to actually introduce the new gauge field, and then we'll see the new operators directly. Yes?
Can't you take any multiple of n for the electric charge to
And-
get q min to be even smaller?
No. Sorry, what?
Like if
The minimum
that
Q,
charge-
the minimum, the Dirac quantization condition is the minimum times the minimum.
But the minimum for q is 0, so
The minimum non-zero one. Yeah. Okay. Good. So in other words, gauging, this is supposed to motivate that gauging Zn1, it took the action, and we just plop in A over N wherever we saw A. And I'll just bring this N out front. And so we can also view this as an action on the coupling constant. So it took E and it mapped it to N times E. Okay? So here's a more general claim that I will not show you. And this is a nice homework exercise if you're up for a little challenge. If the greatest common divisor of NE and NM is 1, then we can gauge ZNE1 times ZNM1 inside the product U1E times U1N, one-form symmetry. So in other words, this subgroup, given this condition, is non-anomalous. That's a fun thing to work out, right? You think there's a mixed anomaly, but if I restrict the fields to be discrete, appropriately enforcing some condition, then that mixed anomaly trivializes. And in this case, the map on the coupling is that E goes to NE over NM times E. This is the maximal subgroup, yes. I mean, that condition is necessary. Okay, so we've got two kind of lemmas or useful things that we built up. One is, yeah, go ahead.
Is there a similar duality like from Maxwell in this theory when we gauge
The question was, is there a similar duality? I think you should, what I'm trying to motivate here is that you should view the action of gauging some discrete one-form symmetry. You just get back to yourself, but with a new coupling. So Maxwell just goes to Maxwell. It's the same theory, but E changes. The quantum theory is sensitive to E, so in general, those are distinct theories. Right? The classical theory is not sensitive to E, but the quantum theory knows about E.
one can't try to derive a strong weak duality?
Maybe be patient for a minute, yeah.
But like the full content is not captured in this E change, right? Because we also have to keep track of what lines we have to keep, right?
The question is the full content captured in this E change? The answer is yes. The full content is captured in this E change. So let me recap the logic a little bit. So when I say that gauging gets you back to Maxwell with a modified coupling, what I mean is that the modified Maxwell theory again has, after I've changed the coupling, I can again say that the minimum charge, the minimum Wilson line is charge 1 and the minimum magnetic charge is 1. Right? So this intermediate step where they were fractions, this rescaled variable now has integer quantization. Right? So you can say that the action is only on the coupling. That's a clean way to think about it.
But if I have the electric particle with charge NE, would it still be the case? If I couple to a matter that is neutral under this?
If you couple it to matter, which is neutral under this, yes, it will still just rescale the gauge field. Okay. Okay, so we have these two tools, electric magnetic duality and gauging discrete subgroups of one-form symmetry, both of which are doing something vanilla. They're just rescaling the coupling in some funny ways. But we can combine them, and that's what I will do now. So we're now ready for the construction of non-invertible symmetry. And we will simply define it by the following composite operation. So I take whatever my theory is. I first gauge ZNE times ZNM. And then afterwards, I do electric magnetic duality. So we can just, at a first pass, view this as some composite action on the coupling. So what is that? E squared over 2 pi, the new value that it will be after I do this transformation, is equal to 2 pi over E squared old. That's just the duality part. And then I get these factors here. NM squared over NE squared. In particular, there's a fixed point if E new equals E old, which I'll just call E then, and that implies that E squared over 2 pi is equal to NM over NE, which is any rational number. Okay? So in other words, this looks kind of like a symmetry. It's some action that I can, some transformation that I can do on the fields. I first gauge this, then I do electric magnetic duality, and the theory comes back to itself on the nose when E is tuned to be a very specific value. So That's how you would ordinarily recognize a symmetry. You would do some transformation on the fields, and if the theory comes back to itself, that's a symmetry. Here we're doing that, but we have all these funny operations in the middle. Okay? So we're going to unpack some of the consequences of this, but just saying that there's some operation that I can do that brings the theory back to itself, that should already strike you as symmetry. Yes?
Related to a question that was asked before, I'm a bit confused why we couldn't ignore the Jacobian factors, the path integral when changing variables.
Yeah, so the Jacobians only are functions of background fields. That's something you can check. So there will be some interesting 't Hooft anomalies, things to think about like that, but the operator valued parts are all 0. More questions? Okay. So if there's one thing you were supposed to take away from my lecture so far, is that if we really want to see a symmetry, we should construct a defect, a topological operator. All right, so let me sketch that out for you. Okay, so what's going to be the picture? So here's going to be our defect. Okay, this is going to be some 3-manifold. You could think of it as all of space if you like, or some other 3-manifold. We'll call it W. And I'll locally say it's specified by the coordinate x being 0, where x is some one coordinate. And here is going to be our defect. dne nm, it's on W. Okay. Here is our Maxwell theory. It has e squared over 2 pi is this magic rational value, nm over ne. And I'll just call this whole thing the quantum field theory T. And AL is the dynamical field. Over here, we have duality of gauge of T, which brings us back to T, because we've tuned the coupling to be particular. And AR is the dynamical field. Okay, so that's the picture. And what do I need to tell you? Right, if you want to understand this construction, so the question we need to answer how does D couple to the bulk left and right fields? All right, so that's our first immediate concern. All right, so this is a codimension 1 operator, so it cuts space into it cuts space-time into 2 pieces. So we can think there are the fields in one region and the fields in the other region. That's what I've called left and right. And there's some kind of coupling between them on D, and we're going to unpack what that is and see how it gives rise to something topological. Okay, so I'm going to pull something out of a hat now, but then we'll be able to verify it. Okay, so here's what I'm going to pull out of a hat. S defect. This is going to be the action on D. It's an integral only over the world volume of the defect, W. And it has various ingredients that I will write. Let me write them and then explain them. Let me even try to get the sign right. Okay, so what is this? So big AL and big AR, I already introduced to you. Those are the bulk fields on the left and the right, and we're just using however they restrict to W equals 0. The cheeky thing in this formula is that A and B, what are those? These are new U1 gauge fields that live only on U. Oh, whoops, we need this. Got to go somewhere else. Now, that looks mysterious, but one thing let me emphasize already is that A and B only have Chern-Simons couplings. Just a minute. So A and B only have Chern-Simons couplings, so there is a chance that they are topological. There's more to check, and I will check it presently, that the defect is topological. But if I had put, some Yang-Mills term for these new gauge fields, something that involved the metric, some contraction, then it would definitely not be topological. So I'm coupling gauge theory, this U1 gauge theory, to some Chern-Simons theory in some way that looks rather artificial, but you'll see why in a minute. Yeah, Oliver.
I was just surprised that there's sort of an asymmetry in how NM and NE appear in there, and that NM is the thing multiplying the new fields, rather than multiplying, say, the.
Yeah, so the question is, why is there asymmetry between the electric and magnetic? After all, I told you that there's some duality even. Actually, there are different presentations of this formula, but like I can integrate in new Chern-Simons fields and integrate out old ones and restore that and make that symmetry apparent. Alternatively, I could have introduced an even bigger action with more fields that was manifestly symmetric, but I choose not to do so. Yes?
In your original, your first lectures, you started off with a charge on a space like.
I'm coming to it.
Oh.
Yeah, I'm coming to it. Yeah.
Also, Chern-Simons usually is ADA, there is ADB.
Good. There's a question about ADA or ADB. Yes. So Chern-Simons exists for both of them, right? So both are Chern-Simons terms.
No, but for both of them, it would be ADA or BDB. But it's more A.
Well, when you have two gauge fields, A and B, the allowed Chern-Simons couplings are an integer quantized 2x2 matrix. Right? If you have one gauge field, it's just ADA. If you have two, you can have ADA, BDB, ADB. You get to choose. I choose this one. Okay, so let's sketch out what's going on with this. Okay. So let's just be bold. I introduced these gauge fields, these new gauge fields, but you could say I don't like them. But the action is quadratic in them, so let me integrate them away. This is a bit of a cheat, but it will help us understand what's going on. The A equation of motion says that NM dB is equal to NE dAL. So if I brazenly substitute that back in, I get I over 2 pi NE over NM integral over x equals 0, or what I was calling W, A left, with D, A right. That looks a much simpler formula. Right? I integrate out A. It enforces a condition on B, which fixes B almost uniquely, which fixes B uniquely, at least classically, from this formula. I substitute back in. Now these mysterious new gauge fields went away, and I just have some direct coupling between the left and the right fields. So given that, you could ask, Clay, why did you write this A and B? This seems to be a very mysterious formula. And the reason I wrote it is that this is an improper Chern-Simons term. If Nm is greater than 1. So strictly speaking, you should understand this action is really a kind of stand-in for this more precise action. But this will be enough for the sketch that I want to give you. Yes, there was a question. The Chern-Simons theory has one-form symmetries. Yes, the defect action itself, I mean, this is telling you, so the question was about what's the one-form symmetry. This is telling you exactly how the one-form symmetry, these couplings, are telling you, in actuality, that's how I cooked this up. This is telling you how the one-form symmetries from the left and the right, which are given by integrals of A left and A right, couple to the one-form symmetries of A and B. So it's telling you how to identify them. That's exactly what these couplings are. It's a good question. Okay, so we'll use this improper quantized Chern-Simons term to really understand what was going on. And now we'll be able to do something quite direct. Okay, so that will be our defect action. What's the full action? The full action is a bulk plus defect contribution. Okay. So S, I need a bigger board. Okay, we have 1 over 2e squared. We'll presently remember that e was particular. Integral over x left less than 0, f left, wedge star f left. F left is dA left. Contribution from the other side of the defect, integral over x greater than 0, f right, wedge star f right. And then we have this defect bit. I on 2 pi NE over NM integral over only x equals 0 of A left wedge dA right. So that's the full action in the presence of this defect. Now what do I do? So I'm going to compute the equations of motion. I'm going to study this system by computing its equations of motion. Let's see how that works. So I'm going to compute the boundary contribution to the equations of motion. Right, so there's a defect, a kind of boundary on the left and the right. So integration by parts is more tricky. We got to keep track of it. Okay. So for instance, if I vary with respect to a left, I find delta S 1 over 2 e squared integral x less than 0. Sorry, the 2 goes away because there's 2 of them. Here's the variation. And then I have the term from x equals 0. Okay. Now we integrate this term by parts, but we track total derivatives because we have some boundary region here. Okay. So here's what would normally be the total derivative. Here's the term you're familiar with. And lastly, this term just comes for the ride. So this term here, this is over x less than 0 still. This is x equals 0. This term here vanishes by the bulk equation of motion. So we continue to enforce that. But this term and this term give us, the first and the third term give us boundary action, boundary equation of motion. What is it? It is that star f left plus I e squared over 2 pi ne over nm f right, this whole quantity restricted to w equals 0, to w, I should say, that is x equals 0, this quantity is 0. That's the boundary term in the equation of motion. And now you start to see a little bit of magic. If this is particular, this particular value, these terms are canceling against each other. So actually, this is just a very simple continuity equation. So here, this is because of our special coupling. So this is a continuity equation. So this fancy defect, its contribution to the equation of motion, is telling you exactly how to glue a left to a right as you cross. Okay, so we are now, let's give this a name. We are now ready, finally, to show you that this is indeed a topological defect.
Is this continuity equation as good as the probably quantized defect action you wrote?
What is the question?
Is it as good, like, is it as proper to define my pattern scroll with that as it is to insert the probably quantized thing?
So this is enough to check that it is topological, which is what I'm going to do. But you will So the question was, could we have just replaced with this, the whole construction? And for the purposes of checking that the defect is topological, in a sense, yes, as you will see. But you need, in order to define a defect, you need to impose this by fields. Right? So, so that's what I've done. I've imposed it by correct topological fields. We can discuss this more afterwards. It's a little bit subtle, but okay, good. So I want to use the continuity equation. Okay, so let's show the defect is topological. Or that the operator commutes with the Hamiltonian, as was asked about. So what do I need? I want that D commutes with T mu nu. Okay. What does that mean? Can take the stress tensor on the left half of space-time, and I want it to be such that when I restrict it to x equals 0, it's the same as when I come from the right. That's what commuting with D means. The stress tensor just freely passes through D. There is no energy and momentum generated by this defect contribution. And we have enough to check that because we know how the left and the right fields are related. So T mu nu takes a very familiar form. Can anybody recite T mu nu? Let's see, are there any real physicists in the audience? Anyone besides Luca and Nathaniel recite T mu nu? T mu nu equals F mu rho nu minus 1/4. Let's be in Euclidean signature, delta mu nu, F alpha beta, right? And there's some factor of E out front in my normalization. Okay, good. In particular, it's continuous. We get continuity via this boundary equation that I derived. Right, so this equation is enough to prove that the stress tensor commutes with the defect. Okay. Kind of an awkward interval. Let's see, I have 5 minutes, but I'm supposed to. Okay. Maybe let me take some questions. After in my next lecture, I'll start by proving that D is non-invertible. So what we have done so far, so we've constructed this D and E and M topological defect. So I have borne out for you that the fact that the action was invariant under this composite operation of duality and gauging this discrete subgroup indeed gives rise to a topological defect, so a kind of honest symmetry in the way that I have been discussing the term symmetry. And what I'm going to show you next, what I'll start with, is that this D is non-invertible. So we will compute D dagger explicitly next time. But let me stop here and take some questions for the last 5 minutes. Yeah?
So can we imagine that we can take like a double scaling limit for A, E, and M, where they are still co-prime, but infinite, then the ratio is finite?
So the spirit of the question is about, isn't it so strange that it's just for rationals? Can't we just take a limit and get some defect for any value of the coupling? You can do something kind of like what you're saying, but I would like to emphasize that there is no continuity in this defect as a function of this rational number. So the algebra that you will write down, I'll write down a piece of it, not all of it, but the algebra that we will write down is not continuous as a function of this rational number. So It's not like there's a smooth limit that's converging to anything.
Right, but I mean, we can claim that any Maxwell theory has an uninvertible.
Well, if the coupling is irrational, then I would not know exactly what you mean. There's a question, yeah.
Just maybe relatedly, could we somehow view that as reaching an integer subgroup that you want generated by pi I instead of the rational number?
I didn't quite understand. Can you say it again?
So in this case, we're gauging subgroups that are generated by like e to the 2 pi, subgroups of u1.
Yes.
Generated by e to the 2 pi I, where 2 pi I is divided by some integer.
Yes.
But you could consider trying to make a subgroup generated by e to the 2 pi I times an irrational number, right? And so this would be isomorphic to the inverse. And could this somehow
Let me say that this is not my first time thinking about these questions. As far as I know, there is no really good notion of symmetry for a general E. It looks very strange that rationals are picked out, but that really seems to be a feature. There are some thoughts, I'd say, in the literature about the more general case, but none of them looks really compelling. So if you have a specific idea, you should try it. Yeah.
you showed us that non-invertible symmetries can lead to selection rules.
Yes.
So would I expect that if I have some correlation functions involving some topological, some lines, there will be selection rules only for special values of E? Like I'm having trouble.
Correct, actually. So the question was, what's going on with the selection rules? So if you just think about the like correlators of the field strength, things that follow kind of that are due to local physics, it will not be sensitive to this. But if you think about correlation functions of lines, Wilson lines, 't Hooft lines, etc., or that's where you see the sensitivity to the coupling. Then there are selection rules that hold only for special values of the coupling. Another thing you can do is you can become sensitive to E not just by the coupling, not just by the Wilson lines, but by putting the theory on a manifold with boundary. So for instance, imagine you have your system and you have some perfect electric conductor boundary. Now again, you'll become quantum mechanically sensitive to E, and there will be degeneracies in the Hilbert space that hold only for particular values of E. This has all been explicitly worked out. Yeah. Oliver, yeah.
I guess I'm still thinking about the question that was asked at the very beginning about how when we do experiments, we can't really see things to an infinite number of decimal places. Is there a sense in which these selection rules would be almost true if E was very close to a rational
Yes,
number?
the selection rules, yeah, the degeneracies the degeneracies are broken a little bit. Yeah, that's right. Yeah.
Okay, because
Yeah.
just
Yeah.
the way the
Yeah.
rational numbers sit in the
Yeah.
reals is this very
Yeah.
complicated thing. And
Yeah.
it seems like you could see there would be all sorts of selection rules from all sorts of rational numbers that you're approximately close to in different ways.
Yeah.
Has anyone sort of tried to understand that?
People have tried a little bit. I mean, I wrote one paper. That's about it. I think it's kind of an interesting question. Yeah. Question here.
What if I add charged matter? Does this defect survive at least for some subset of?
The question is, what about charged matter? That's the second thing we're going to talk about after lunch. So the answer is yes. Some parts of it will survive. Yeah.
It seems like NE and NM being co-prime was important for the anomaly, for it to be anomaly free. But what's stopping me from like first gauging N electric, and then I have my new theory, and then gauging N magnetic with the same N? It seems like that would be a way.
That's the nothing operation. I invite you to check that that's the nothing operation.
And that's different than just.
Yes, that is different. Yeah.
Maybe the construction of the defect, we also want to say how it acts on some other operator.
Yes, I did not say that yet. So people are asking about selection rules. We're going to get to that. Yeah, so far I'm just trying to get to the fact that there is a defect, that it's non-invertible. Then we got to find the selection rules. We got to say what happens with matter. We got to figure out some more details. But yeah, we're getting there. Yeah.
So I know that the electromagnetic duality will be different in 3 dimensions, but is there a similar statement in 3 dimensions as opposed to 4?
There are analogous constructions in 3 dimensions, but the spirit is a little bit different. one thing that was special in 4 dimensions, which also happened in Hotat's lecture when he talked about the compact boson in 2 dimensions, is that in 2D, when you gauge a discrete, say, N0 form symmetry, you don't destroy it. It just pops back as a new ZN0 form symmetry. That's why the compact boson can be invariant under gauging. And here, something similar is happening. We're gauging a ZN electric 1 form symmetry, say. And we don't lose that symmetry. It comes back to us in a new magnetic form. And that's why the theory can be invariant under gauging. Yeah?
Is there a role of conformal symmetry somewhere here? Because 4D Maxwell is conformal, the 2D examples were all conformal.
Good question. No, there is not. I will construct an example in an interacting non-conformal theory after lunch. Yeah?
If we had a theta term, can we play the same game as S of 2Z?
Great. So the question is, what about the theta term? Absolutely. People have studied that.